Hi everyone, welcome to my YouTube channel. Today I will be talking about Six Sigma product design. In complex assemblies, which there are many interacting components and dimensions, we need to prevent tolerance stack-up problem. Here, 5 parts are assembled with these dimensions and tolerances. The final assembly target is this gap, called Y, with dimension 1.695 plus minus 0.1 millimeter. The question here is how we can set specifications on each component to ensure that the final product after assembly meets specifications and have reasonable process capability value for the assembled device. I suggest you to watch the video of process capability analysis for normal and non-normal data before watching this video to get familiar with terminologies. Okay, to answer this question, one approach is to check the tolerance stack-up problem using Monte Carlo based simulation for tolerance analysis and define each dimension as a random variable and assume all dimensions are independent and normally distributed. This assumption completely makes sense because components are coming from different suppliers. Then, using CPK values for each dimension that we get from supplier and the tolerance ranges, we can get the standard deviation for each dimension. Then, we use nominal value as mean and calculated standard deviation to build the normal distribution for each component. And finally, use Monte Carlo simulation to find DPPM for final assembly target and predict the number of assembled devices which will be out of the specification limit defined for device performance. I will cover Monte Carlo simulation for tolerance analysis in separate video, so then we can talk more in details. In this effort, the assumption is that the tolerance ranges USL and LSL are given by product design team, and we get CPK value from supplier for each component. Otherwise, we cannot do Monte Carlo simulation. So what if those dimensions are not properly toleranced by product design team? Then all predicted values for DPPM will be wrong. So how we can decide what specification and tolerances to use to predict the number of DPPM? What if the supplier offered different tolerance ranges? Which one we should use? Here, cost issue come into the game. So it's a trade-off of multiple things to decide which specifications to set for the component. Here we have 5 main components which impact on the target gap value on the final assembly. With these specifications on the components and the gap of Y equal to 1.695 plus minus 0.1 millimeter, is this a Six Sigma product design? So we would like to answer this question. Let's assume the nominal value and variance of x1, x2, x3, x4, and x5 are known here. The goal here is to determine the proportion of parts that meet the specification on overall gap of Y equal to 1.695 plus minus 0.1 millimeter. The dimension of final assembly gap is A1 multiplied to x1 plus A2 multiplied to x2 until A5 multiplied to x5, which A1, A2, A3, and A4 are equal to -1 and A5 is 1. So if xi, our dimension, is normally and independently distributed with the mean of the mu I and variance of sigma I, then y normally distributed with the mean of this and variance of this. Remember that mu I and sigma I are known for each component as given here. So as we said, the y is normally distributed with a mean of 1.695, which is a combination of all dimensions. And the total variance is the summation of all these variances, which gives us the standard deviation of 0.0469. So the fraction of assembled items falling outside the specification can be determined with cumulative probability distribution function. To find the fraction of components that are within a specification, we must evaluate these probability. Let's switch to Minitab and find these probability. Go to probability distribution plots and select the normal distribution. Put the these value for the mean and 0.0469 for standard deviation. Then go to the shaded area, select the x value, and then the middle. The LSL is 1.595 and USL is 1.795. And finally, hit the OK. So the result shows that 96.7% of assembled component will fall within the specification limit. And in total, it is predicted 33,000 devices will fall out. This is not a Six Sigma product design. From this table, you can see that the process capability ratio for 33,000 is about 0.7. Let's change the specification limit on the target value to 0.50 mm. We can make this number bigger as long as the device performance not affected. In Minitab, change the USL and LSL right here. The cumulative probability is 99.86%, which means 1,400 devices will fall out. So we see that even under this scenario, the product is not a Six Sigma design. The process capability ratio in this case is something between 1 and 1.1. Let's change the specification limit on the target value to 0.2 mm. As we mentioned, we can make this number bigger as long as the device performance not affected. So here, change the USL and LSL. As we can see, the DPPM for this simulation is 0. So this design is a Six Sigma design. The goal of the Six Sigma is pretty high, but it is good to have a Six Sigma thinking. Please note that the process mean is still subject to disturbances that could cause the mean to be shifted by as much as 1.5 standard deviation of the target value. This situation is shown here. Okay, going back to the original question. This design is not a Six Sigma product design for y equal to 1.695 plus minus 0.1 mm. Since the DPPM is more than 33,000. So, how to set a specification limit on the individual components of assembly so that a specification limits on the final assembly will be satisfied? Suppose that we want to set the specification limits to fall inside the tolerance limits of the process for the final assembly so that CP is equal to 2. Approximately, for the final assembly. The gap on the final assembly is normally distributed. As a Six Sigma product, this implies that the natural tolerance limits must be located at mu y plus minus 6 sigma y. In this scenario, mu y is 1.695, so the process is centered at the nominal value. Okay, the maximum possible value of sigma y that would yield an acceptable product is 0.0166. So sigma y must be less than this number. So if sigma y is less than this number, then the number of non-conforming assemblies will be acceptable. Okay, let's see how these affect the specifications on the individual components. The variance of gap of the final assembly is the summation of all sigma squares and equals to 0.000277. Here I assume sigma for component 1 and 4 is the same and call it sigma square. I also assume sigma 2 is half of the variance of sigma 1 and 4. And variance for sigma 4 and 5 is 75% of variance of part 1 and 3. So from these equations, we can easily find the sigma value. And then we can find the sigma 1, sigma 2 till sigma 5. So here, this sigma value can be translated into specification limits on the individual components. So this is Six Sigma product design. Okay, let's look at another example which includes defining a permissible clearance between two parts. In this case, let's look at clearance between shaft and ball bearing. This approach could be applied to any other example. The internal diameter of bearing, defined as x1, is normal random variable with mean of 20 and variance of 0.05 square. The external diameter of the shaft is x2, which is normally distributed with mean of 19.74 millimeter and variance of 0.03 square. Here is the assembly. When these two parts are assembled, it's obvious that interference will occur if the shaft diameter is larger than ball bearing diameter. So if x1 minus x2 is less than 0, then interference will happen. Let's name x1 minus x2 as variable y, which is the clearance between two parts. Please note that the distribution of y is normal, with mean of 0.26 millimeter and variance of 0.0034, because it's a combination of two components. So we can easily find the probability of interference, which is cumulative probability of y less than 0, which is 0.000036. This indicates that very few assemblies will have interference, almost 4 defects per million. This is essentially a Six Sigma design. In problems of this type, we can define a minimum clearance C such that the cumulative probability distribution of clearance less than C is equal to alpha. The alpha level is defined by designer as 0.0001, which means 100 defects per million. And C becomes the tolerance for assembly and can be compared with design specification. From Z distribution and having alpha value, we can find the Z value, which is 3.71. Then, with solving this equation, we can calculate the permissible clearance C, such that only 100 parts per million will have clearance less than 0.043 millimeters. Okay, let's talk about products with nonlinear dimensions. There are many examples of products with nonlinear dimensions. One of the cases is a spring clip on PCBs. The amount of force applied on a spring clip due to deflection has huge correlation with stability of the signal. So it needs to be in a specific tolerance range to work properly. The other example is air cylinder. The force applied is function of pressure multiplied by area. The tolerance range on the force depends on tolerance range on pressure and area. The third example is Ohm's law. The voltage equals to resistance multiplied to current. These are examples of products with nonlinear dimensions. In the first example, F equals to K multiplied to X power N. In the second example, the force is equal to pressure multiplied to A. And the third example, the voltage is equal to current multiplied to resistance. The question here is how to do Six Sigma design for products with nonlinear dimensions. Consider a simple DC circuit component like this. Suppose that the voltage across the resistor is 100 plus minus 2 volts. The specification on the current is 25 amp plus minus 1. And the resistance is 4 plus minus 0.06 ohm. We assume that variables I and R are normally and independently distributed, with means equal to their nominal values. So mu I is 25 and mu R is 4 ohms. We know the relation between voltage and current and resistance is V equal to Ri, which is a nonlinear combination. It's multiplication of two variables. We can approximate the nonlinear function V equal to Ri by linear function in the region of interest by Taylor series. From this equation, we can find the mean of voltage, which is the first term, and the variance of voltage. So I is normally distributed variable with the mean of the mu I and variance of the sigma I squared. And R is normally distributed variable with the mean of mu R and the variance of the sigma R squared. We want to have 2700 ppm for both I and R, which it means alpha equals to 0.0027 for current and resistor. In this equation, 26 is the largest possible value for the current, which is a 25 plus 1, minus the mean value, which is a 25. And sigma I is the variance of the current that we are looking for. Please note that alpha need to be divided by 2 because of having two tails, two-sided distribution. With having of the z value equal to 3, the sigma I would be 0.33. The similar approach for the resistor. 4.06 is the largest possible value for the resistor, which is 4 plus 0.6 minus the mean value, which is 4, divided by sigma R, that we are looking for it, equals to z value. From this calculation, the sigma R equals to 0.02. With having mu R, mu I, we can find the mean value of voltage. And also, we can find the variance of the voltage, which is equal to 1.99. So the probability that the voltage will fall within the design specification is around 84%. So this means that only 84% of the observed output voltages will fall within the design specifications. Note that the natural tolerance limits can be calculated in this way. Mu of voltage plus minus 3 times of the standard deviation equals to 100 plus minus 3 times of the standard deviation. The result is 100 plus minus 4.23 volts. And the process capability of the output voltage is 0.47. We have the upper specification limit, we have the lower specification limit divided by 6 times of the standard deviation of the voltage. So, please note that even though the individual current and resistance have CP of 1, which means 2700 defects per million, their interaction produce a circuit whose performance relative to the voltage specification is very poor. The CP is equal to 0.47. Is much less than CP equals to 1 for each of those variables. Alright, we covered the design for Six Sigma in this video. Please don't forget to subscribe to this channel if you like to watch more videos like this. Thank you. We are going to release video series on different topics including application of statistics in manufacturing and quality control, robotics and mechatronics, industrial machine vision, system dynamics, finite element analysis with abacus, GD&T and tolerance analysis, and many other interesting topics. Don't forget to subscribe to this YouTube channel to get notified when a new video on this topic is released.